Hello, my name is Louis Flynn, and I am from the Free University of Brussels, and I'm here to present on the active transformable prosthesis that we've built within the Cyberlegs project, which is an P7 project. And we've adapted it towards use in the Cybathlon, which is what I'm going to talk about today. It's our first fully integrated transfemoral powered prosthesis, meaning we're able to provide energy to both the knee and the ankle. And we do this by utilizing SCAs everywhere. So we have a lot of springs, and those spring constants are tuned by using normal gait kinematics and torques in order to determine these constants so that we can minimize the amount of energy that we're using in our motors. So we try to do this as much as possible using these passive springs, and then only use our motors to modify our gait cycle rather than. So we have a combined orthoprosthesis system within the Cyberlegs project, and so when this was originally developed, it was developed to work with both an orthosis side and a prosthesis side to assist dysvascular patients who might be weak in the limb that hasn't been amputated. And so we have a communication system between all of them, which we control using a wearable sensory apparatus. So we had IMUs on the entire body and foot-sole sensors to measure center pressure on both the prosthetic and the orthosis side. And so when we had to adapt this towards the Cybathlon, we had to redo a lot of the control systems for this. We used a McKeppel-based ankle, which is a mechanically adaptable compliance drive. Although in this system, we've replaced the mechanical adaptability and replaced it with a parallel spring because we wanted to reduce our peak torques in our ankle and reduce the motor requirements that you can see here, and increase our velocity of our moments arm a bit. The way the ankle actually works is that we have a moments arm that's here that pulls on a linkage that compresses the spring as you. So if you plantar flexion or dorsiflexion, we can compress that spring. And then underneath the ankle joint, we have a parallel spring here. So that only works it only provides a plantar flexion torque. It's much like a biome, actually. Our knee drive is divided up into 3 different major systems, which we call our weight acceptance system, which is on the back of the knee here. And that is counter to our knee drive system, which is on the front of the knee here. And the weight acceptance system is in the system primarily to actuate right after heel strike to provide the spring-like behavior of the knee after heel strike. And then we also have an energy transfer system, which ties the knee and the ankle together. And on the bench, we can get this to actually work quite well. We have a weight acceptance torque provided here, so you can see it follows the natural torque angle characteristics quite accurately. And our energy transfer is able to provide quite a bit of the extension torque required during the push-off phase of walking. The baseline spring here, this blue one, is this green spring on the front of the actuator. And the idea here was that we wouldn't need to ever move our main drive during normal walking because the spring would just passively act in the front. But if we wanted to adjust the behavior of the system, we could adjust it by moving the motor up and down and injecting more energy or taking it out as we see fit during the weight acceptance phase. The control system that we built for the Cybathlon is a very simple system. It's a finite state machine where we have different user-selected values on the controller and its arm. And this is because we don't have our intention detection system from the Cyberlegs system to use for this project. So we're using only IMU rate gyro inputs from the residual limb, and using a pseudo-integrator system, phase control system, in order to control both the knee and the ankle. And yes, we can also detect when our foot is on the ground or when we're pushing on our foot through the use of our series elastic actuation in our ankle. So that's what we're using for our ground detection system. We have also a number of, after each of these modes are selected, we have multiple sub-modes in our state machine for each of these different actions that are controlled by these. So, in terms of behaviors for the Cybathlon, we can show that we were able to perform quite a few of the tasks, including level ground walking, sit-to-stand walking, slope walking, and the hurdles. And we have some comparisons in this video of how our pilot tackles these same things with his sea leg. He has a relatively short residual stump and can't balance on his leg at all. It is with his current prosthesis, and is able to tackle some of this a bit more naturally than with his current prosthesis. So. The one thing that we really cannot do very well is the stepping stones event. So I don't know if all of you are familiar with the events of the Cybathlon, but there's a stepping stone event where there's a small stone that you have to step on, but it's rounded, and it's something that requires a lot of balance. And this is the one thing that he cannot really do very well. So we'd like to thank all of our supporters and just say that this was our first attempt at making a device, and we are continuing the Cyberlegs project in the future, and with our consortium